Thanks, Deepthi. Okay, is my screen visible?
Yes, go ahead.
Cool. Okay. Welcome, everyone. In the next 20 minutes or so, we are going to discuss Presto DB and Apache Hudi and how they integrate. My name is Sudha. I am a PMC member in the Apache Hudi project, and along with me here is Brendan. Let's get to the agenda. We'll be talking through a Hudi, like introduce Hudi, give a high-level overview, and dive into table types and queries that Hudi support. And Brendan will be talking about Presto Hudi integration and how that has evolved over time. And finally, we'll talk about some interesting roadmap items that may require deep integration with Presto. Cool. Apache Hudi is a data lake storage system that allows organizations to build and maintain petabytes data lake. It brings stream style processing on batch data by giving 3 simple primitives, upserts, deletes, and incrementals. And let's see how this works. I've used an illustration here. As you can see, writes can be streamed, and these are usually RDDs of records, and usually inserts, updates, or deletes. They're streamed into a Hudi table. And queries can leverage this Hudi table. We have 2 types of queries: a snapshot query that exposes the latest version of latest value of all records in that table, and an incremental query which pulls changes since the last time. So for example, give me all changes that happened as of time t. So these are the capabilities of Hudi. Hudi supports upserts like we discussed previously, but to make it faster, we use indexing schemes, and these indexes are pluggable. Like with any other production environment, writes can always fail. And to handle that, Hudi allows to publish writes atomically, and in case of failure, it provides ways to roll back as well. To tackle concurrency, Hudi provides snapshot isolation between readers and writers, where writer would be an adjacent job and a reader would be query engines like Presto, Spark, Hive, or Impala, etc. Hudi provides with save pointing capability, where save points are basically snapshots of table as of a given point in time. This comes in really handy when there are like disastrous situations and you really want to revert the table to like a safe state, like a safe known state. And Hudi tries to carefully size the files and lays them out using statistics. It can compact both columnar and row-based data using async compaction. And it also maintains a timeline metadata of the table. What that gives you is like really what changes happen to the table at a high level. Cool. So with all those capabilities, what Hudi offers is basic building blocks to build a data lake system. Let me dive into this picture here. Hudi is compatible with any DFS type storage like HDFS, S3, Azure, GCP, etc. And it provides like a couple of tools. Here you can see a Delta Streamer tool that aids in ingesting data from various different sources like Kafka, like microservices sending data to Kafka, or like source of truth data coming from Cassandra, MySQL, etc. What Delta Streamer does is captures these like data and formats them in a way that Hudi understands and stores them into the data lake. While storing them, there is no really any transformation. These can be like, typically these are like raw tables. And these raw Hudi tables can then feed onto incremental pipelines that build like model tables. And both the raw tables and the incremental tables are then available for all the query engines to query. Cool. I think I gave a good enough intro to Hudi, but let me dive into more on table types and queries. Just before getting in there, a little overview of these concepts would help understand the table types and queries. So there are 3 main components to a Hudi table. One is the data files themselves. These are columnar files or row-based files. We use Parquet for columnar and Abro for row-based files. And then there is indexing component, which basically gives the mapping between a record ID and a file ID. And The third critical component is the timeline metadata. We spoke about this briefly, but what it gives you is how you reason about the changes that a table went through. For example, at time T1, writes happened, at time T2, a compaction happened, time 3, there were some more writes happened, and so on. So in this picture, you would see like typically a Spark data source is written like ingested into the Hoodie table, and the ingestion takes care of touching all these components, and that helps serving the like the primitives that I discussed earlier, the upserts and incremental primitives. And then these are available to all these query engines. Cool. So really table types define how data is indexed and laid out. And there are two main table types, copy on write and merge on read. Copy on write is purely columnar formatted data, Parquet. And what happens in copy on write is inserts are neatly packed into new files. Whereas say if there are updates to those files, the already existing files, right? Like the records in that files, those are simply like versionized and rewritten. That's what happens in a copy on write update. For merge on read tables, these can be both columnar data and row-based data. So what happens is like updates are kind of logged to what we call as delta files. These are the log files that has Avro-based data, and to aid in quick ingestion. And then later a compaction process kicks in to kind of merge both these Parquet data and Avro data and produce as new versions of columnar data. So that is merge on read table. There are three different queries. One is a snapshot query, incremental query, and last one is read optimized query. Snapshot queries expose the latest snapshot of records in a table as of a given time. What this means for merge on read table is the queries actually read both the Parquet table and stitch the Avro data on top of that on the fly. For incremental queries, this is like exposing changes that happen as of a given time. So this is really useful to feed on incremental pipelines, like feed change streams to the incremental data pipelines. And read optimized queries are exposing snapshot of a table, but they only come from the latest columnar data that is available. So the query might not have the most recent data in case of a merge on read table where the data went to a log file. But what it guarantees is like pure columnar performance comparable to any non-Hoodie columnar table. Okay, so let's get to a quick visualization of how these queries and table types work hand in hand. So here I have a copy on write table. This visualization shows the ingestion and queries on copy on write table. As you can see at the very beginning, there were like 5 records, and Hoodie decides to put them across 3 files. And then there is a batch of updates. And for copy on write table, you can see the files are rewritten as file, like for example, here AB would be the file 0 and file 1 are rewritten as file 0 prime and 0 file 1 prime. And then this keeps happening for every batch of updates. And if you see the queries, you'll see that the snapshot query at any point in time reads the most recent value for all the records, whereas incremental queries would just give the changes that happened since the previous time. So for example, at time T1, you would see the incremental query would just yield A prime and D prime. So that's what happens in a copy on write table. Moving on to merge on read table. So here, inserts, like at the very beginning, there are inserts and 3 new files are created. These are Parquet files. And as updates happen to these files, new log files are being created, which are Avro format. And there are more updates, and you'll see that even certain inserts are tacked onto the log files. This is Hoodie basically trying to size the files to accommodate like file sizing mechanisms and stuff like that. And compaction, what it does is basically stitches all these together and produces a new version of columnar data for the as the time goes. And this keeps happening. If you see the queries, the snapshot query at any point in time will always give the latest values for all records. And read optimized queries will just give the data that is available as from the most recent columnar data. So by that, what I mean is like at time 0, you would see A, B, C, D, E are the most recent data, and time 1 also A, B, C, D, E. But after the compaction, the latest values are exposed since the compaction kind of stitched all that updates together in a new columnar data. And like incremental is same as what I explained in COW previously. Cool. With all these, you can ask me, how do I choose a table type? So to get into that, we need to understand certain trade-off between copy on write and merge on read table. So these, like the data latency is higher in copy on write table because of the Parquet ingestion and having to rewrite the files every time. Whereas in merge on read, we simply append the updates to a log file. So data latency is kind of lower. The update cost is higher because of the rewriting in copy on write. And for merge on read, it's lower. The write amplification is kind of higher in copy on write because even for a few bytes of update, we'll have to rewrite the entire file. This is again lower on the merge on read side. So if you really want to like have a replacement of your existing Parquet table, there aren't a lot of updates, and you understand your workload, it's pretty smooth, there's no busty traffic, and you do not really worry about having real-time data, then copy on write is probably the best choice. But it's bound to Parquet ingestion performance. But on the other hand, if your workload is like pretty unpredictable, or you need more flexibility, you need quicker ingestion, and you do care about fresher data, then merge on read is probably the right choice. Okay, with that, I hand over to Brendan to talk about Presto Hudi integration and how that evolves so far.
Thanks, Sudha. Hi, I'm Brandon from the AWS EMR Hoodie team, and I'll be continuing the presentation with the evolution of Hoodie Presto. So the first step in Hoodie Presto integration was to make the standard read-optimized Hoodie queries work. These are the queries that query just the base Parquet data. To do this, Hoodie introduces its own input format class for integration with Hadoop apps such as Presto or Hive. Even with this input format, integration with Presto was not immediately straightforward because at the time, Presto did not use the splits directly from the input format. Instead, Presto has its own Parquet split loader implementation. Presto's split loader needed to call getSplits on this Hoodie input format, or else it would read all the Parquet data in the table path and not only the latest file versions. As Hoodie keeps multiple versions of Parquet files, this could result in duplicate data. The Hoodie community recognized this, and based on Presto community suggestions, opened a PR to make this work way back in 2017. This PR allowed Presto to call inputFormat.getSplits when it saw the use of the newly introduced use file splits from input format annotation. Hoodie added this annotation to the Hoodie input format, and then basic Hoodie queries could then work through Presto. At the time, Presto had no Hoodie dependency, so this was achieved by dropping the Hoodie Presto bundle jar in the Presto Hive plugin directory. But there is room for improvement here. The call to input format getSplits was costly. It made many RPC calls to the name node. Presto is required to know the file status and block locations for each of the input splits returned. This added 2 extra RPC calls to the name node for every split, times the number of partitions loaded. Further, for every partition loaded in the Presto split calculation, getSplits on the Hoodie input format would be invoked. This caused redundant Hoodie table metadata listing, which otherwise could have been reused across partitions. Instead, Sudha here introduced a PR for the Hoodie RO table path filter, and Presto took a compile time dependency on Hoodie. This Hoodie RO table path filter would filter the versioned Parquet files for Hoodie to allow queries to work through Presto without calling getSplits. Additionally, the path filter was able to cache listing results in order to further improve query performance for these Hoodie read-optimized queries. Presto Hoodie integration, however, still had more to be done, which brings us to Presto support for Hoodie snapshot queries. As Sudha described, Hoodie provides a snapshot query system. This allows you to query the most recent snapshot of your data containing real-time updates. To accomplish this, Hoodie merges the base Parquet data with an Avro update log containing the most recent updates to the data. The extra complexity of merging the data from two sources requires a custom file split and custom record reader, and is the reason that up until recently, Presto did not support these snapshot queries. So, how is this supposed to work? As mentioned earlier, Hoodie introduces its own input format class. This Hoodie input format has two methods, getSplits and getRecordReader. In the case of the Hoodie real-time input format, the format used for snapshot queries, the getSplits method returns a custom Hoodie split containing the extra metadata describing the associated Avro log. The getRecordReader method returns a custom record reader that has the logic to merge the Parquet with the Avro data to give you the end result. Hive, for example, calls both of these methods out of the box. Presto does not, as it has its own native equivalents for querying Parquet. As I described earlier, some time ago, the Hoodie team introduced a special annotation, use file splits from input formats, that tells Presto to call inputFormat.getSplits. This allowed read-optimized Hoodie queries to work, but the Hoodie record reader was still not used. Presto's vectorized Parquet reading was used instead, which was fine for these read-optimized queries, but not compatible with the extra logic for snapshot queries. Hoodie tables currently use the Parquet Hive Serde. In Presto code, this triggers the use of the Parquet page source, which does not use this getRecordReader method from the input format. So, what changes do we need to make to allow real-time queries to work in Presto? So let's look at these blocks here. The Hoodie team, back in 2017, has already added the use file splits from input format annotation to cover this first block of getting splits. So now we need to allow Presto to use the Hoodie record reader for reading splits. But we also have another step we need to resolve before we can do this. Presto Hive has the concept of the Hive split class. Presto converts whatever split it gets into this serializable Hive split cast so it can be easily passed around. Because Hive split, by default, only takes the standard Hadoop file split fields, it misses any extra data contained in custom file splits. As the Hoodie real-time file split has some of these custom fields, we need to make sure this gets included in the Hive split. To do this, we added a custom split converter interface, which takes the custom split and returns an easily serializable map containing this extra metadata. We can then include this map in instances of the Hive split class. This custom split converter interface also has a method for merging the standard file split fields with the custom split map in order to return back the original file split. With this combination, we can include the Hoodie real-time file split data within the Hive split and then build it entirely back again once passed around. So now that we have the Hoodie real-time file split back, this middle box is taken care of, but we still have to use the Hoodie record reader. As I mentioned earlier, Hoodie's use of the Parquet Hive Serde triggers the use of the Parquet page source, which is not what we want, as it does not call getRecordReader. To work around this, we added another annotation, use record reader from input format, which when seen by Presto, skips use of the Parquet page source to instead use the Hive record cursor class. This class uses the record reader from the input format, completing our chain at the bottom here and allowing Presto snapshot queries to work. One last thing to note is that these snapshot queries take a different code path than the standard Hoodie queries, so that performance improvements, such as Suda's path filter, are not affected. So, now that Hoodie Presto snapshot queries work, what's next? I will let Sudha take that.
Yeah, thanks, Brendan. So I'm going to talk you through some interesting projects that we are working on, and we believe these may need deeper integration in Presto as well. So here we call them RFCs in Hoodie. So here's our first RFC, RFC 12, that talks about how to efficiently bootstrap larger tables into Hoodie. So the current version of Bootstrap that we have allows for partial migrations or wherein the older partitions are not like Hoodie, does not support Hoodie primitives like upserts and incrementals, whereas the newer partitions are completely Hoodie, what completely Hoodie supports. And if you need full support for the entire table, we ask users to rewrite the entire data set. And as you can imagine, that would be time consuming because of the data copy. So to make this more efficient, the next gen Bootstrap project is to see how we can do a zero copy rewrite of the entire table. By that, what we mean is like we'll be laying out skeleton Parquet files that would have the Hoodie metadata and kind of internally reference to the the data files from the previous source table. So as you can see here, the splits get even more interesting, and this is where we could probably leverage what Brendan described for the snapshot queries. We could leverage that changes in Presto to also support these complex splits in the Bootstrap project. And we have the next thing is like incremental queries and time travel queries. These are already supported in Hive and Spark. For Hive, we pass these configs to the Hadoop conf, and we're thinking about how to support them in Presto. If custom session configs are not like possible to be passed on to Hadoop conf, then an initial idea is maybe we can register the same table in a new name. That way, incremental queries can hit that table, and probably use the the query predicates to get other information that are needed for incremental queries. But we definitely welcome any ideas if you guys have through our RFC process. The next project is improvements in query planning and listing. You can see the full RFC here, linked in RFC 15. What this aims at is avoid listing as much as possible. So Hoodie writes and reads require the list status operation, and this can be really expensive when we talk about large data sets that has like huge number of partitions, and each partition has like huge number of files. So Hoodie already maintains this metadata on files, like what files went into what operation and sort of that part is already there. What we're looking at is to consolidate all of that into like a metadata snapshot, so we can avoid listing by leveraging that. And while we are building the data infrastructure for this, we are also thinking about exposing range stats for columns, and that would aid in pruning queries effectively. So this is yet another area where we are looking into see how Presto can leverage this. I think Hive exposes this via table stats. Maybe something like that would help. Probably like building a new Presto Hoodie connector would help. We're still exploring these ideas in Presto. And the last project that I wanted to talk about was record level indexes. So I already spoke about upserts, and these are like a popular operation in write operation in Hoodie. To make them even more faster, Hoodie leverages indexing. And what indexing does is basically tag, like provide a record ID to file ID mapping. So it can easily tag incoming records as either updates or inserts. We have existing index implementations like Bloom filters, key ranges, and HBase implementation as well. Bloom filters are maintained in the Parquet data files footer. So, but these come in at a cost when we speak about really large data sets. For example, consider a non-partitioned Hoodie table where for upserts to work, and like every Bloom filter in all the files have to be scanned to kind of use the indexing. This can be like really expensive. So we're looking at introducing another index implementation, record level index, and this would be native in Hoodie. The reason again is like with the HBase implementation, some users in the community feel that it could be operationally overhead, like operating another system entirely. So that record level index would also try to tackle that by like a native implementation in Hoodie that Hoodie can maintain. It would consider like pluggable storage like H files or rock3b for keeping this index. We believe it would be much faster to scan these few index files rather than scanning like all of the Bloom filters and all the data files. And we believe this would improve the upsert performance way more for large data sets. So this again is another area where so far we haven't used the indexing on the query side to prune or like avoid listing so many files. But this is again another area where we are looking at using this in the query side as well. Cool. With that, these are the resources. If you have any ideas, suggestions, or have questions, please feel to connect with us. And we're really excited to work in these communities. And we can open up for questions.
Great. Thanks, Sudha and Brandon. There are a couple of questions that have come in, so I will read those out for you. So the first one is from Arun. Where is the timeline metadata stored, and how different is this from table stats?
Right. So the timeline metadata is stored in the .hoodie folder, and the table stats would also be stored along in the same directory structure. Like partitions will have their own partition level stats, and table level stats would be stored in the .hoodie partition.
All right, thank you. And then the next question, I think, Brandon, you may have answered it, but I'll ask it here. Do you use native Avro SERDI, so serialization, deserialization?
Oh yeah, I mean, I mentioned that we register the Hive table as using the Apache Hive Saturday.
Okay, got it. All right, I think those are a couple of questions, folks. If you have more questions, please go ahead and ask them in our Q&A, the Q&A panel that you see at the bottom. Sudha and Brandon, thanks for sharing. If you can go ahead and stop sharing, we'll move on to our next session.